Welcome back. Let us do one more example for the solution of partial differential equations by direct integration. So consider the question. Solve dou square z by dou x square plus z is equal to 0 given that x is equal to 0, z is equal to, given that when x is equal to 0, z is equal to e raised to y and dou z by dou x is equal to 1. That means when x is equal to 0, z is e raised to y, and when x is equal to 0, dou z by dou x is equal to 1. So in this problem, we have the partial derivative is dou square z by dou x square. So that does not contain y. That means here we have now partial derivative containing now partial derivative with respect to y. Okay, so here what we are going to do is, here we suppose that if z is a function of x alone. Okay, first we consider, suppose z is a function of x alone. That means for this problem we consider this kind of problems if the equation does not contain the partial derivative with respect to y. Now in that case, first we consider z as a function of x alone. So if z is a function of x alone, then the ordinary derivative and partial derivative are same. So if z were a function of x alone, in that case we consider the given partial differential equation as an ordinary differential equation. That is, we consider this equation as an ordinary differential equation d square z by dx square plus z is equal to 0. So which equation we can rewrite as d square, capital D square plus 1 of z is equal to 0, where d is equal to d by dx. You have already studied the ordinary differential equations. So in that case, in the case of ordinary differential equation, you know how to form the auxiliary equation. So the auxiliary equation is m square plus 1 is equal to 0. This implies m square is equal to minus 1. So m equal to plus 1 or minus 1. So in that case, the solution becomes z is equal to c1 cos x plus c2 sin x, where c1 and c2 are arbitrary constants. But if we consider z as not a function of x alone, or z is a function of both x and y, considering this fact, we choose c1 and c2 as an arbitrary function of y. That is, here z is a function of both x and y, hence we consider c1 and c2 as functions of y. Hence we can modify equation 1 as z is equal to f1 of y sin x plus f2 of y cos x. So here we have c1 cos x plus c2 sin x. Write first as sin x, then cos x. So we write z is equal to f1 of y sin x plus f2 of y cos x. So let me choose this as equation number 2. Now we have to apply the given conditions. So we have obtained z as a function of x and y. So we have obtained the solution. Now the given conditions are for finding the arbitrary functions f1 and f2. Now first condition is when x is equal to 0, z is equal to e raised to y. So when we apply that condition in equation 2, we get e raised to y is equal to, we put x is equal to 0. So sin 0 is 0. 0 plus f2 of y into cos 0. So cos 0 is 1. So you get e raised to y is equal to f2 of y. Now differentiating equation 2 partially with respect to x, since our second condition is given in terms of dou z by dou x. So dou z by dou x is equal to f1 of y into derivative of sin x is cos x plus f2 of y into derivative of cos x is minus sin x. So we have taken that as equation number 3. Now we are going to apply our next condition, that is when x is equal to 0, dou z by dou x is equal to 1. So substituting that condition in equation 3, we get one is equal to f1 of y into cos 0 minus f2 of y into sin 0. Now cos 0 is 1. So you get 1 equal to dou z by dou x is 1. So 1 is equal to f1 of y into 1 plus f2 of y into 0. So you get f1 of y is equal to 1. Now substituting the values of f1 of y and f2 of y in equation 2, we get z is equal to 1 into sin x plus e raised to y cos x. So our answer is z is equal to sin x plus e raised to y cos x. So which is our required solution to our problem. So I think all of you have got an idea about the solution of partial differential equation by direct integration. Thank you.